Welcome to Antarctica, the continent at the end of the Earth, where life seems to be frozen forever. A harsh, bone-chilling land, seemingly ruled by only ice, snow, and freezing winds. But hidden deep beneath the eternal ice, Antarctica hides terrifying secrets, shocking discoveries, enough to astonish the world. Are you ready to join us in uncovering the mystery of this icy door? Antarctica today, a frozen land covered almost entirely by kilometers of ice, a place where life seems to struggle to survive. Average annual temperatures are below freezing, fierce snowstorms can last for weeks, and sunlight is almost absent during the long winters. A stark, isolated landscape, it seems impossible to believe that this was once a completely different world, a land teeming with life and warmth. But it is in this silence and eternal ice that the past speaks, a silent symphony recorded in ancient rocks and sediments. These are fossils, priceless traces of the creatures that lived and thrived on this continent millions of years ago. These whispers from the past not only shed light on Antarctica's complex geological and biological history, but also bring shocking surprises that completely change our perception of this planet. Let's turn the pages of this frozen history together, to listen to the stories told by petrified leaves, ancient bones, and footprints imprinted on rocks, silent witnesses of a lush and vibrant Antarctica. One of the most important and most surprising fossil discoveries in Antarctica is the finding of dinosaurs. Dinosaurs, giant reptiles that dominated the Earth during the Mesozoic era, an era that lasted from about 252 to 66 million years ago. The discovery of dinosaur fossils on a frigid continent like Antarctica in the late 20th century truly shocked the paleontological world. In 1991, Argentine paleontologist Dr. Eduardo Olivero discovered the fossil of a small theropod dinosaur on James Ross Island in the Antarctic Peninsula. This dinosaur, later named Cryolophosaurus ellioti, lived during the early Jurassic period, about 194 million years ago. Cryolophosaurus was notable for its unique fan-shaped bony crest on its head, which was probably used for mating or other species recognition purposes. The existence of a relatively large carnivorous dinosaur at such a high latitude during that time suggests that the Jurassic Antarctic climate was much warmer than it is today, enough to support a complex ecosystem. After Cryolophosaurus, many other dinosaur fossils continued to be found in Antarctica, including giant herbivorous sauropods, hadrosaurs, and sauropods. These discoveries add to the growing body of evidence that Antarctica was once part of the supercontinent Gondwana, a giant land mass that included most of the continents of the southern hemisphere today: South America, Africa, India, Australia, and New Zealand. During the Jurassic and Cretaceous periods, Gondwana was geographically distinct, with much of its landmass, including Antarctica, located in temperate to subtropical latitudes. This warmer climate allowed for a rich flora, as evidenced by the abundance of ancient plant fossils found across Antarctica. Scientists have unearthed fossils of giant ferns, gymnosperms of the ginkgoales and cycadales groups, and most notably, fossils of Glossopteris, an extinct genus of angiosperms with tongue-shaped leaves that is one of the most important pieces of evidence supporting the theory of continental drift. The widespread distribution of Glossopteris fossils in Antarctica, South America, Africa, India, and Australia suggests that these continents were once connected. In addition to dinosaurs and plants, scientists have found fossils of many other animals in Antarctica, including ancient marine reptiles such as plesiosaurs and mosasaurs, ancient birds, and even early mammals. These discoveries paint a diverse picture of the life that once existed in Antarctica, from giant sea creatures to tiny land animals. So what led to the climate change and the disappearance of these rich ecosystems in Antarctica? The answer lies in the geological movement of continents and global climate changes that took place over millions of years. According to plate tectonics, the Earth's tectonic plates are always moving, albeit very slowly. Antarctica, which used to be located at a lower, warmer latitude, has gradually moved towards the South Pole. As the continent approaches the pole, it begins to experience colder climates, leading to the formation of ice caps. The glaciation of Antarctica took place over millions of years, beginning around 34 million years ago in the early Paleogene period. The formation of the Antarctic ice sheet was a complex process, influenced by factors such as changes in the Earth's orbit, changes in greenhouse gas concentrations in the atmosphere, and the circulation of ocean currents. As ice accumulated, it reflected sunlight back into space, increasing the cooling effect and promoting widespread glaciation. The climate change and the formation of permafrost caused a mass extinction in Antarctica. Plants and animals that could not adapt to the new harsh living conditions gradually disappeared, giving way to creatures that could better withstand the cold or were forced to migrate to warmer lands. The fossils we find today are the last vestiges of a lost world, whispers from a green and vibrant past. Fossil discoveries in Antarctica are not only valuable in reconstructing the continent's ancient history, but also have great significance for studying past global climate change. By analyzing fossils and the sediments they contain, scientists can better understand the relationship between climate change and mass extinctions, and thus make more accurate predictions about the potential impacts of climate change today. The existence of a liquid, hypersaline lake amid the icy, arid lands of Antarctica's McMurdo Dry Valleys, there exists a strange and haunting natural phenomenon that has captured the attention of scientists and captured the imagination of the public. It is called Bloodfalls, a dark red stream as if fresh blood seeping from the Taylor Glacier and pouring onto the white surface of Lake Bonny. First discovered in 1911 by Australian geologist Griffith Taylor during the Terra Nova expedition, Blood Falls initially caused much controversy and mystical explanations. Many believed that this strange red color was due to the growth of red algae in the glacial meltwater. However, later scientific studies have uncovered the secret behind this creepy appearance, revealing a unique geochemical and biological story hidden deep under the thick layer of Antarctic ice. The secret of Blood Falls lies in the source of the red water. It turns out that this water is not ordinary glacial meltwater, but hypersaline brine water that has been trapped beneath the Taylor Glacier for millions of years. This underground lake, located beneath about 400 meters of ice, is thought to be the remnant of an ancient sea that was isolated as Antarctica gradually froze over. During its millions of years of isolation, the water in this underground lake has undergone complex geochemical processes. It has become extremely iron-rich due to interactions with minerals in the underlying rock. When this hypersaline water finds a crack in the glacier and seeps to the surface, it is exposed to oxygen-rich air. The iron oxidation process occurs immediately, turning the soluble iron ions into insoluble iron oxides, or simply put, rust. It is these iron oxides that stain the water red, creating the iron-rich water trapped in a cold and dark environment, like the one below the Taylor Glacier, that raises interesting questions about the viability of life in such extreme conditions. Scientists have conducted many studies to analyze the chemical composition of the Blood Falls water and search for traces of microorganisms that can survive in this environment. The research results have shed light on a unique bacterial ecosystem, capable of surviving without sunlight and relying on chemical reactions to create energy, chemosynthesis. These bacteria are thought to have been isolated in the underground lake for millions of years, evolving independently and developing special biochemical mechanisms to adapt to the iron-rich, oxygen-poor, and extremely salty environment. One of the important biochemical processes these bacteria use is sulfate reduction. In an oxygen-depleted environment, these bacteria use sulfate dissolved in water to oxidize organic matter, releasing energy and creating sulfides. These sulfides can then react with metal ions, including iron, to form various minerals. The study of the microorganisms in Blood Falls is of great scientific significance. It provides us with insights into the possibility of life in extreme environments on Earth and opens up the potential for the search for extraterrestrial life, especially on cold celestial bodies with signs of subsurface liquid water, such as the icy moons of Jupiter and Saturn. If life can survive in extreme conditions like those beneath Taylor Glacier, then perhaps it can also survive in similar environments elsewhere in the universe. The study of Blood Falls also poses significant technical challenges. Accessing and sampling the water from the subglacial lake beneath the thick ice requires specialized drilling and sampling equipment, capable of operating in extremely low temperatures and high pressures. Scientists have used advanced techniques such as ice piercing and underwater robotics to explore this mysterious environment. Detailed chemical analysis of the Bloodfalls water has revealed a complex composition, including a variety of dissolved ions such as sodium, chloride, sulfate, and especially iron. The salt concentration in the water is many times higher than that of seawater, allowing it to remain liquid even at temperatures below its normal freezing point. The interaction between the iron-rich hypersaline water and the overlying ice is also an exciting area of research. Scientists are investigating whether this water affects the stability and rate of melt of Taylor Glacier. Subglacial channels of liquid water may play an important role in the dynamics of Antarctic glaciers. Bloodfalls is not only a unique geochemical phenomenon, but also a window into an ancient ecosystem, isolated and evolving in the dark for millions of years. It is a testament to the incredible resilience and adaptability of life, which can find ways to survive even in environments that seem inhospitable to us. The strange appearance and fascinating scientific story behind Bloodfalls have made it a symbol of the mysteries that Antarctica still holds. It reminds us that even in the most inhospitable places on the planet, there's still much to explore and learn, secrets waiting to be revealed beneath the permafrost. In the vastness and silence of the icy continent of Antarctica, where white and blue dominate the landscape, there is a special gift from the cosmos that regularly visits: meteorites. These drifting rocks, remnants of the formation of the solar system 4.6 billion years ago, or fragments ejected from other celestial bodies, such as the Moon and Mars, have traveled millions of kilometers through space to eventually land on the icy surface of Antarctica. What makes Antarctica such a paradise for meteorite hunting is not only its vast area and relatively clean ice surface, but also the unique natural mechanism that helps concentrate these space visitors. As meteorites fall and become buried in the ice, the slow flow of ice over time moves them towards the transantarctic mountain ranges or the melting areas along the coast. In these areas, ice is eroded by wind and sublimation, exposing the meteorites trapped inside. The stark contrast between the dark black of most meteorites and the bright white of ice and snow makes them easier to spot than in other locations on Earth, where they can be hidden among rocks and vegetation. This has made Antarctica one of the richest meteorite mines on the planet, attracting scientists from all over the world to search for and study these messengers from space. Since the first meteorite was found in Antarctica in 1969, tens of thousands of specimens have been collected, representing a diverse collection of compositions and origins. These include chondrites, the most common type of stony meteorite, which contains small spherical grains called chondrules, considered the original building blocks of the planets. They also include achondrites, stony meteorites that have undergone melting and differentiation on their parent planet, similar to volcanic rocks on Earth. Particularly interesting are the finds of meteorites originating from the Moon and Mars. These samples, ejected from the surfaces of these celestial bodies by large impacts, have traveled through space before falling to Earth. Studying lunar and Martian meteorites allows scientists to directly analyze the chemical and mineralogical composition of other worlds, providing invaluable information without the need for costly on-site missions. Lunar meteorites found in Antarctica have helped scientists better understand the geological history and composition of our natural satellite, from ancient plateaus to younger basalt seas. They provide evidence of the massive impacts that shaped the Moon's surface and reveal details about its crust, mantle, and core. Similarly, Martian meteorites, identified by the composition of trapped gases in them that matches the composition of Mars's atmosphere measured by the Viking spacecraft, have provided insights into the red planet's geological history, climate, and potential for life. Some Martian meteorites, such as ALH 84001, have even sparked major scientific controversy over their potential to contain fossilized traces of ancient bacteria, although these claims are still being debated. The study of meteorites in general, and Antarctic meteorites in particular, is of great importance to many scientific fields. They provide pristine samples from the dawn of the solar system, helping scientists learn about the original chemical composition of the cloud of gas and dust that condensed into the sun and planets. They also provide information about the formation and evolution of planets, asteroids, and comets. In addition, analysis of the mineralogical and chemical composition of meteorites can reveal the origins of water and organic molecules on Earth, which are essential ingredients for life. Some theories suggest that meteorites and comets delivered the seeds of life to our planet in its early stages. Scientists use a range of advanced analytical techniques to study Antarctic meteorites, including scanning electron microscopy, SEM, mass spectrometry, X-ray diffraction, and a variety of chemical and isotopic methods. These analyses help determine the mineralogy, elemental composition, age, and thermal history of these space samples. The collection and preservation of Antarctic meteorites is also carefully done to avoid contamination from the Earth's environment. Specimens are usually collected with clean gloves and stored in special bags and containers under cold, dry conditions to protect them from deterioration. In addition to its widely accepted and proven scientific discoveries, Antarctica is also a fertile ground for mysterious stories and controversial theories. Among them, claims of ancient man-made structures buried under the permafrost or suddenly exposed by melting ice. Satellite images and blurry photographs circulating online have fueled speculation that an advanced prehistoric civilization once inhabited the frozen continent, a past forgotten under thousands of meters of ice. These images often show straight lines, regular geometric shapes, or structures that appear to be of enormous scale, reminiscent of pyramids, walls, or even ancient cities. The appearance of these shapes in such a harsh and isolated place as Antarctica has raised many questions. Did a mysterious civilization once conquer this land in the distant past, when the climate may have been warmer? Or are these just tricks of nature, optical illusions created by erosion and light? One of the most controversial structures is an image of a supposed three-sided pyramid near the coast of Antarctica. These photos have gone viral on the internet, attracting the attention of both conspiracy theorists and the scientific community. Many believe that this is evidence of an ancient civilization that built great structures similar to those in Egypt or Central America. However, the scientific community has largely dismissed these claims, offering explanations based on natural geological processes. Antarctica is home to complex rock formations that have been subjected to intense erosion by wind, ice, and continuous freeze-thaw cycles over millions of years. This erosion can create strange shapes, including peaks that resemble pyramids. Photographic angles and lighting conditions can also create optical illusions that make natural structures appear man-made. Another common phenomenon in eroded rock formations is the formation of steep planes and sharp edges due to cracking and erosion along weak planes of rock. When viewed from a certain angle, these geological features can be mistaken for walls or man-made structures. In addition, the phenomenon of pareidolia, the human brain's tendency to recognize familiar patterns in ambiguous images, also plays an important role in explaining these discoveries. We tend to see familiar shapes like faces, animals, or man-made structures in clouds, rocks, or other random images. This may explain why some people see pyramids or structures in images of natural terrain in Antarctica. To unravel these mysteries, scientists have used a variety of research methods. Geologists have conducted detailed terrain analyses, using high-resolution satellite data and field surveys to study the structure and composition of suspected structures. Glaciologists have also studied the movement and erosion of ice to better understand how ice may shape the Antarctic landscape. An important tool in studying subglacial structures is ground-penetrating radar, GPR. This equipment emits radar waves into the ground or ice and records the reflected signals. Variations in the reflected signal can indicate the presence of different layers of material or buried structures. Although GPR has been widely used in Antarctica to study ice structures and subglacial geology, to date there has been no published credible scientific evidence of ancient man-made structures under the ice. It is important to note that the scientific community is open to new discoveries, but extraordinary claims require extraordinary evidence. Until there is clear, independently verified physical evidence published in reputable scientific journals, these ancient man-made structures in Antarctica remain in the realm of hypothesis and speculation. However, the existence of these stories and images still piques the curiosity and imagination of the public. They remind us of the mystery and the unknown that our planet still hides. Antarctica, with its complex geological history and harsh environmental conditions, may still hold exciting scientific surprises in the future. In the seemingly lifeless, icy landscape of Antarctica, there are some very special oases of liquid water, hypersaline lakes. In contrast to the thick layers of ice that cover much of the continent, these lakes remain liquid all year round, despite the harsh freezing temperatures, thanks to their extremely high salt concentrations, far exceeding the salinity of any ocean on Earth, even saltier than the famous Dead Sea. One of the most famous examples of this strange phenomenon is Don Juan Pond, located in the McMurdo Dry Valleys, one of the driest places on the planet. Don Juan Pond is famous not only for its record-breaking salinity, but also for its small size and shallow depth. Surprisingly, the lake does not freeze even when the air temperature drops very low, a testament to the power of salt to lower the freezing point of water. The extraordinary salinity of Antarctica's hypersaline lakes is the result of a complex combination of geological and climatic factors. Over millions of years, chemical weathering of the surrounding rocks has released dissolved salt ions into the water. Due to the extremely dry climate, much more water evaporates than is replenished by snowmelt or rain, which is rare, leading to a buildup of salt over time. Repeated freezing and thawing also contribute to the increased salt concentration as the frozen water removes pure water, leaving behind a more concentrated salt water. The existence of these hypersaline lakes in Antarctica raises a fascinating question. Could any life survive in such an extreme environment? With salt concentrations so high that they crystallize on the lake shores, low temperatures, and a constant lack of oxygen, these lakes would seem to be an inhospitable place for most familiar life forms. However, scientific research has shown that life can still find ways to survive, even in the most extreme conditions. Scientists have discovered a unique microbial ecosystem in hypersaline lakes in Antarctica, including species of salt-loving bacteria and archaea. These microorganisms have developed special biochemical mechanisms to cope with the extremely high osmotic pressure caused by salt concentrations, as well as other harsh environmental conditions. One of the adaptive strategies of salt-loving microorganisms is to accumulate compatible solutes inside their cells. These substances, such as glycerol, betaine, and amino acids, help balance the osmotic pressure between the inside and outside of the cell, preventing dehydration caused by hypersaline environments. In addition, these microorganisms have developed special enzymes and proteins that can function stably in high-salt environments. Their cell membranes also have a unique structure to maintain their integrity in extreme conditions. The study of microbial ecosystems in Antarctic hypersaline lakes is not only important for expanding our understanding of the limits of life on Earth, but also has important implications for the possibility of extraterrestrial life. The extreme environments of Antarctic hypersaline lakes have many similarities to potential environments for liquid water on other bodies in the solar system, such as subsurface lakes of Mars or subsurface oceans of saltwater on the moons Europa and Enceladus. Understanding how life can adapt and survive in such extreme conditions on Earth could provide important clues for the search for life on other worlds. If life can thrive in the cold, oxygen-poor, hypersaline lakes of Antarctica, perhaps it can also exist in similar environments elsewhere in the universe. Scientists have used a variety of methods to study Antarctic hypersaline lakes, including measuring the physical and chemical parameters of the water, analyzing ion and organic matter composition, and using molecular biological techniques to identify and study the microorganisms that live in the lakes. Water and sediment samples are carefully collected to avoid contamination and analyzed in laboratories with state-of-the-art equipment. Other notable hypersaline lakes in Antarctica include Vanda Lake and Wright Lake, also located in the dry valleys. Although not as salty as Don Juan Lake, they are still much saltier than seawater, and also harbor unique microbial ecosystems. Lake Vanda is particularly interesting because it has a distinct temperature stratification structure, with layers of water at the bottom being much warmer than the surface, a phenomenon that is not fully understood. You want to learn something new every day? This channel is for you. Subscribe to get the latest tutorials and lessons.